Hello everyone, welcome to the 7th week of interaction session for Control Systems course. My name is Soumya and I'm a PMRF PhD student at IIT Gandhinagar. And last time, though there was no attendance because of the preponement of the class, so that time, if you have gone to the recordings, it was a session on root locus, very basic questions. In that, you did not even have to draw the whole root locus. It was like you find the breakaway points, then you can find where are the poles located, you find the number of asymptotes, the angle of asymptotes, and so on. So that was a very basic question, but in the end we saw a MATLAB code that could help you to generate the root locus. So it was essentially the use of rlocus command in MATLAB. So today also we'll have more questions on root locus, and it would be a more in-depth approach to find that what kind of uh, what behavior do we get for closed loop poles, provided that we are given open loop transfer function and we go on varying the gains of the system. So yeah, last time there was a question where we had a unity negative feedback system, and then we had k greater than 0, which was the ideal case. This time we would have different cases also. You might have seen in the lecture that there are cases when k is less than 0, or it is a positive unity feedback system. So essentially the transfer function changes and the nature of the root locus also changes. So we'll see that, but before that, a brief recap of what root locus actually helps in, or what it does is. So yeah, it is a graphical technique. You might have already seen from the lecture also that it is a graphical technique that essentially helps you to know that how the poles of a closed loop system change as the open loop gain varies. So you already have an open loop transfer function. Let's say it have an open loop transfer function. Let's say it is GS into HS. This is your open loop transfer function. Okay, you know very well that you already have, if you have some k here, and this k is the gain, which with characteristic equation. So essentially, if this is your case, as in this case also, so k, sorry, I wrote this here. Yes. So what would happen if it is of this type? So how would the poles move? Closed loop poles move. So if we start with the very basic concept, so let's say we are given a system whose characteristic equation is defined by this equation. Okay. If your characteristic equation is this, then from here you can compare that this GS into HS is only the term which is written here. 1 plus GS HS is equal to 0. So this is valid for system where k is a positive constant, positive parameter, and the characteristic equation is given in this way. It is a unity negative feedback system. Let's assume this. Now you know where are the poles, where are the zeros according to this. What we do initially when we want to construct the root locus, we try to find out what are the open loop zeros and poles in the complex plane. So what do we essentially find out? Let's say this complete term, this term is GS into HS. It is some numerator upon some denominator. This will give you the open loop zeros, right? This would give you open loop poles. So we do find out that where are the open loop zeros and open loop poles placed in the complex plane. Then we also know that how the root locus branches will emerge. So it is like that, let's say there are some number of like curves which are going to emerge. Then note that each of the n curves, n is what? What is n? It is the total number of poles. N curves in the root locus will start from an open loop pole for k is equal to 0. So always at open loop pole only you're going to have k is equal to 0, and then you're going to have k is equal to infinity for an open loop 0. So essentially, the branches would emerge from an open loop pole, terminate at an open loop zero. If sufficient number of open loop zeros are not present, then they will go to infinity. So there comes the concept for asymptotes and everything that we'll discuss again. So out of these, M curves will terminate at open loop zero. For example, you have n is equal to, let's say, 3. You have m is equal to 1. That means what? You have 3 poles. This means you have 1, 0. That means for one pole, we have 1, 0, right? But for 2 poles, we do not have zeros, so they will terminate at infinity. So this is the way it works. The remaining n minus m curves will go to infinity in the complex plane along asymptotes. Okay. Then what we want to do? We
Ma'am,
want to find out where is the root
ma'am,
loci located on the real axis. Or do you want to say something?
yeah, ma'am. Sorry for interrupting, ma'am, but one of my friend is joining, ma'am. Please do add her, ma'am. Abhinaya, ma'am. Her name is.
I do not see any request. Has she joined some other link? There is no request on
No.
my side.
Okay, ma'am. Yeah, I'll try it.
Yeah. So then we want to find out that the root loci is. So we want to find out if the root locus is where exactly on the real axis we have the root locus. So this is determined by the open loop poles and zeros that lie on the real axis. So we'll see in this case, we choose a test point and then we see that if the number of poles and real poles and zeros on the axis to the right half of this test point is odd, then it lies on the root locus. That point essentially lies on the root locus. So we'll see that with the help of example also, because we have to mark the points where we have root locus exactly on the real axis. Okay. Then the third thing is that we want to find out where are the asymptotes. So essentially we need to find out what are the number of asymptotes. Number of asymptotes should be determined by n minus m only directly. And then you're supposed to find out at what angle these asymptotes should be. So asymptotes should be the lines that would lead the branches to go to infinity. So this can be determined with this angle, and there would be definitely some intersection point of asymptotes. So that would be given by sum of open loop poles minus sum of open loop zeros upon n minus m. Okay, these will be more clear with the questions also. We saw some questions in the last session, but we'll have more questions today. Then we are supposed to find out the breakaway and break-in points. So when do they occur? The breakaway or break-in point would occur between two consecutive poles or two consecutive zeros. So essentially the thing is, so you know very well that the branches are going to emerge out from the open loop poles. So let's say if there are two consecutive open loop poles and there is no zero in between. So if they are together and they do not have any zero in between, that means there is no like termination point in between. तो zero पे जाना ही नहीं है. So it is going to happen कि poles से दो branches would emerge, they would meet at some point and break away. That means one would go in one direction, one would go in other direction. But they'll not be terminating at each other. So that sort of thing. So we want to find out what is the breakaway, and break-in point is if from some complex poles, let's say there are two branches coming and they want to terminate at zeros on the real axis, they would come to the real axis, they will break in and they will split the sides. So we'll have this question related to breakaway and break-in points also. It would be more clear. So that point is found out using this equation. Then if we have complex poles, we want to find out what is the angle of departure and what is the angle of arrival. So if it is for pole, it is angle of departure. If it is for zero, it is angle of arrival, right? Because from pole only the branches depart, at zero only the branches come. Then we also want to check, okay, if I know where the root locus is going on the imaginary axis, does it cross the j omega axis or the imaginary axis in the S plane? So for that we want to determine the points where the root locus may cross the imaginary axis. And that is simply done by putting S is equal to j omega. When you substitute S is equal to j omega in the characteristic equation and then you solve for omega and k, you'll essentially see where are the points it actually intersects. Okay. Then we sketch the root locus. But there was another scenario that was discussed with you, and that was if we have positive feedback system. If we have positive feedback system, so you know this concept, right? That for negative feedback system, what do we have? 1 plus gs into hs is equal to 0, right? For positive feedback, what do we have? 1 minus gs hs is equal to 0. So we have these differences, right? So here is the minus sign, which is also reflected here, the same minus sign. So if this were the case, you got something with positive feedback. So there could be two cases when you could have these minus sign. One is अगर positive feedback system है तो ये definitely minus sign होगा. The other thing is when k is negative. When k is negative, let's say we will say that okay, k is positive for me only, but I will change the characteristic equation to this form, right? This could be also one of the situations. So if k is negated or it is a positive feedback system, it would fall into this category. All right. Then what we are going to see is that here we'll do mostly the same things only. It would have some changes only in 3 points. One is that we would check that if we choose some test point on the real axis and want to find out if that part where the test point is chosen, does it lie on the root locus or not, or does root locus lie on that part of the line or not. Then in that case, we'll have to see that all the poles and zeros to the right of it, real poles and real open loop zeros definitely to the right of it should be even. In the earlier case, it was odd, right? Here it is even. Then we also want to find a number of asymptotes. Number of asymptotes would be given by same n minus m, but the angle of asymptotes would be different. It would be defined by this. In the earlier case, it was plus minus 180 degree to k plus 1. Here it is k into 360 degree upon n minus m. That's the only difference. Then we also want to locate the angle of departure and angle of arrival. So here this is 0 degree. In that case, you saw that it was 180 degree. So this is the difference. So related to the first part, this part, the first root locus part, we already had a question in the last class. Today, the questions will be mostly dealing with will be this part. Yeah, we'll be dealing with would be this part, and it is very similar to the one that we had discussed. So in case you have missed that class, this would again help you completely. So what we are going to do? Okay. So let's begin with the question. So this is an open loop transfer function of negative feedback closed loop system. Okay. So I have got something negative feedback. That means it is sure that I'll have to use this method. Open loop transfer function, which is 1 plus GSHS is equal to 0. So from here you can see that it falls in the first case only. But see the later part. The open loop transfer function is this, where k is non-positive real valued parameter. K is non-positive. That means what? K is less than 0. If this k is less than 0, definitely it goes into this, where you can say that whatever k is here, that is positive, but I have taken the minus sign. So it would follow the second thing. So the first case was only valid when we had negative feedback system with k greater than 0. Any other case that you have, whether the feedback goes positive or k becomes negative, both of them you're supposed to use this condition and the rules corresponding to this open loop transfer function. Okay, so now we'll start. So this is your open loop transfer function, right? Here. Here open loop transfer is function is k into s plus 1 upon s cube plus 2s square plus 2s. If you try to find out the 0, I hope everyone is now very comfortable with determining what is the 0 and what are the poles of the system. So if you try to find out, so it is not 0, don't say system 0, it is open loop 0. Okay, this is open loop pole of the system. What is the open loop 0? It is -1, right? You take numerator is equal to 0. What are the open loop poles? So the equation is s square plus 2s plus 2. Can someone solve and tell me what are the open loop poles? We want to make this 0 and then we want to find out what are the poles of the system. How many poles would be there? Since it is some order 3 polynomial in the denominator, it is going to have 3 poles, right? Now what are the poles? What are the poles of the system? Has anyone solved?
-1 plus or minus j, madam.
Right, and one is 0. Don't forget to have 0 here. So there are 3
Yes, ma'am.
poles, 0 and -1 plus minus j. So these are the poles of the system. Now what we want to do is we'll have it plotted all over. So this is sigma, this is j omega, which is real and imaginary. Then what we'll have, where is the pole? One pole is at 0. The other pole is as -1 plus j. So this is essentially -1 plus j. Other is at -1 minus j. And there is a 0 which is at -1. So here, the 0 is over here. So all the zeros are denoted by the circles, and the poles are denoted by just a second. Yeah, all the zeros are denoted by circles and the poles are denoted by crosses. This is general convention that we follow. So then what we want to do is, so this is 0, this is -1, right? We want to find out the region on the of the real axis that does not lie on the root locus. Which region does not lie on the root locus, that we want to find out. So what was the thing that we had read about it? We had read that a test point should be chosen if the total number of real open loop poles and real open loop zeros, mind it, real open loop poles and real open loop zeros, lie to the right of this test point is even, then that point lies on the root locus. So if we try to see, so let's say we consider this region. Okay, so we are talking about this pole right now. So if we check in this region, have a test point, we are not talking about this pole. Let me remove this. Okay. We are talking about this region. If we have some test point here, how many poles and zeros do you have to the right of it? It is 0, right? And 0 is not even number. Okay, so this part, yeah, this part is, just a second. No, we'll consider this part. If it is 0, then also we are supposed to consider. Okay, so this part lies on the root locus. Now let's say if we check for this part and we have a test point here, we have a pole to the right of it. That means the number of open loop zeros and poles that we have to the right of it is 1. That means it does not lie. Now if we check this part, the number of open loop zeros and poles that we have to the right of it, the real open loop poles and zeros are 2. That means this lies. This lies, this lies, this does not lie. Okay, so since this part does not lie on the root locus, so what is the region of the real axis that does not lie on the root locus is, so it is -1 to 0. So this is your answer. Okay, so from here you know that, okay, anything I am not supposed to do between this, there cannot be anything between this going on the real axis.
Madam,
Yeah.
once go to that question, madam. A pole at zero, yes, ma'am. Pole at zero terminates at -1, madam.
Pole at 0
Once
terminates.
draw the root locus, madam. Once draw the root
Let
locus.
me complete the whole step. It is just the beginning. You're supposed to just find out that which lies. So we'll have a number of steps and then we'll be constructing the root locus also. But
Madam, thus -1 plus j will go to infinity along +90, and -1 minus j will go along in infinity through -90 degrees. But how the pole at 0 reduce comes to -1, madam?
yeah, I'll tell you. Wait, we have the questions in sequence. That will answer all your questions.
Okay, madam.
So see, it is a continuation of problem one only. So in this whole thing, you will be able to draw the root locus. That is why it is in this way. So in the second problem, we can see is that which of the following statements is true. So how many asymptotes it would have? Essentially, this is the question first. If you are able to say what is the number of asymptotes, you'll have to find out what is the angle of the asymptote, right? So how do we determine this? So yeah, before that, number of asymptotes you can directly say no, n minus m is n minus m. So, and what was n? It was 3, right? What was m? It was 1. So you are going to have 3 minus 1, that is 2 asymptote. Now, how are these asymptotes be? How will these asymptotes look like? Like at what angles it would be? So angle can be given by what? Angle is given by this formula, plus minus k into 360 degree upon n minus m. So if we want to write what is the angle of asymptotes, it would be uh, plus minus 360 degree into k upon 2. So it would take you to 180 degree, where k is 0, 1, 2. First, let's put k is equal to 0. Okay. So what it would be? It would be 0 degrees. And yeah, it would be like, if you consider this thing, it would be plus minus 0 degree, essentially in both the directions. So minus 0 degree is 180 degrees only. So you'll have two asymptotes. Okay. One would be along this direction. One would be along this direction. So anywhere poles, whatever poles are there, here was a pole, I guess, and here was a 0. So something is sort of this is going to happen where let's say you're going to have some sort of this thing where this would act as an asymptote and this would act as an asymptote. ओके तो ये जो तीन पोल हैं इनमें से जो भी ब्रांचेस निकलेंगे डेफिनेटली टू ऑफ देम वन ऑफ देम विल टर्मिनेट एट दिस जीरो एंड टू ऑफ देम वुड गो along these asymptotes to infinity. तो अभी देखते हैं कि वो कैसे जाने वाला है बट दिस वुड हैपन फॉर श्योर. Okay, then in the third question we have, yeah, uh, which is true which one of the following statements is true about the locus of the closed loop poles? Okay, so what is going to happen? Is it going to have some break-in point, breakaway point, or what is going to happen? Okay, so we'll be answering that question. So in that case, you are given the formula, but before that, I'll tell you this thing. So what are the, how do you understand that if there would be breakaway or break-in point from intuition? So if there are two consecutive poles, you would understand कि हाँ उससे branches निकलेंगे, they would come at some point and both of them would go in the other direction. Okay, so let's say, sorry, if you have let's say a pole here, a pole here, a branch would emerge from here, a branch would emerge from here. They both will meet here. One will go in this direction, one will go in this direction. So this is called a breakaway point. Okay. In the other case, if you have one, these both were poles, it is not zero. Okay. A pole here, a zero here, and let's say two poles here. Two poles are present here and a zero is present here. Then there are, so one has to go to infinity, one has to go at zero. So these both poles would come, they would come closer. This would go to this zero, this would go to infinity. So this is called break-in point. So if poles are in general repellent in nature, but they are attracted by the zeros. So this is what is important. So breakaway points typically happen when there are multiple poles close to each other. As k increases, these poles repel each other and move away from the real axis to the complex plane. Whereas for break-in points, it occurs when there are zeros on the real axis. So you saw here there was a zero. They move towards each other. The poles move towards each other. So you saw they both were moving towards each other from the complex plane, and as k increases, converging to the real axis. They have converged to the real axis. One moved in this direction, one moved in this direction. So this was the way. So it happened in this way, right? So the next question, so in this question, we are supposed to find out that which one of the following statements is true about the locus of the closed loop pole. So we want to determine if there is one breakaway point of there, or there is some break-in point. So in that way, so you can see here there are two poles present over here. In our case also, there are two poles. There is a zero over here and there is a pole over here. So it could be a case of break-in point, but let's see what is going to happen. So how we'll start? You know this already. I don't know, someone is joining the meeting, then immediately leaving. Some sort of this is happening. Is it some problem from my end? Should not be a problem, I guess. Okay. So, okay. If we see the characteristic equation, then 1 plus k into as upon bs. So this is basically representation. So gs into hs can be written as some as upon bs. Okay. So this is a characteristic equation. This is equal to 0. Now, yeah, in our case, it was 1 plus k into s plus 1 upon s cube plus 2s square plus 2s is equal to 0, right? So what we had actually read, I think I might have some snippet. Don't I have? No, I haven't taken from this. So you have already seen this as I showed. We need to find out derivative corresponding. We need to find out the root of this equation. Now why this? Why do we do this? Because we want to find out where are they breaking in or breaking away. Means the gradient is going to change. So for that, what we do is, if this is the equation, we essentially do dk upon ds. That is the only thing which is written here and nothing different. Okay. So yeah, we want to find out where the derivative is changing suddenly. Now, what we will do here is, we will find b dash s first. It is 3s square plus 4s plus 2, right? The derivative of the quantity in the denominator, it would be this. Then if as is already known, a dash s is what? It is 1, right? So if we try to Right. What is b dash s into as minus bs into a dash of s is equal to 0? So it would be 3s square plus 4s plus 2 into as would be s plus 1, right? Then bs would be s cube plus 2s square plus 2s into a dash of s, which is 1, is equal to 0. I want to know what are the roots you're going to get for s. Like you can observe from here that it is going to be some sort of third order. You will have something s cube plus something s square plus something s plus something is equal to 0. So you'll have three values, three roots for this equation. So can you tell me what are the values of s? If we are able to find out what are the values of s, and if we get k corresponding to this s to be positive, if we get it, then that means that it is a break in or break away point according to the question. So let's find out what is the value of s. Please solve this question. You can just simplify it and use some polynomial root finder. Don't find the root on your own. But if I'm not wrong, the coefficient should be all of this. This is 2. This should be 5. This should be 4. And this should be 2. See if you're getting the same answer. And tell me what are the roots of this equation.
Minus 1.65, 0.42, minus 1.42, and minus 0.42.
You might have some imaginary terms also, no? Like minus 0.42, you're right, but it should have something plus minus, no?
Yes, ma'am. Plus 0.65 share.
Okay, right, very good. So there would be two, so it would be minus 1.65 and minus 0.42 plus minus 0.65 j. So these are the roots. Once you have them, we need to check if these are really the break-in or breakaway points or not. And for them, we need, for this confirmation, we need to know that corresponding to every root that you have, if we are getting k is equal to k greater than 0 or not. This is the essential test. So you can see, so this is your equation. This was your equation, right? So from here, you can find out the value of k also. So for s is equal to minus 1.65. Okay. Your k turns out to be, just use this equation only. So your k is uh, minus of s cube plus 2s square plus 2s upon s plus 1, right? This is your k. And put s is equal to minus 1.65. Check what is the value of k. You would get some value of k. We need not worry what is the value. We need to check the sign for this value. So just substitute s is equal to 1 minus 1.65 and you will obtain some value here. And I'm sure that value would be greater than 0. It should come like 3 point something or somewhat of that sort. But this term will be positive. This number would be positive. Okay. Similarly, you are supposed to find out for s is equal to minus 0.42 plus minus 0.65 j. You find out the value of k. If you can see directly, that if you substitute this value, this s value over here in the k value, matlab minus of whatever pole you had, let's say we call it s1. So s1 ka cube plus 2s1 square plus 2s1 upon s1 plus 1. You can very well see that this would turn out to be imaginary value. Okay, it would not be real value. So you can see that this would be some imaginary value, this would be some real good value, and it would be greater than 0. So we'll be only accepting this value and we'll reject this value. So what we know, this is a break-in point because we have got the value of k which is greater than 0. So this is definitely a break-in point for us. So break-in point hone ka matlab, we saw earlier, where did we see that? Yeah, these were the poles. So definitely they are going to come along this way. From this pole also this is going to come here. It was minus 1.65, I think. Have I drawn what were the poles and zeros for this equation? Just a second. I'll draw this again here, okay, so that it is even clearer. So see, you had a pole here, right? Yeah, a 0 here, a pole here, minus 1 plus j, a pole here, minus 1 minus j. What would happen? And where did you get this break-in point? At minus 1.65, means somewhere here at this point. So what would happen? From here, you would come here, you would come here. You'll also have to calculate the angle of departure. That is essential to know what is the direction of root locus movement from the complex poles. It would come here. One of them would move to 0, the other would move to infinity. And for this pole, it would move this side. So what we had seen earlier, where are the asymptotes? Asymptotes were along this way and along this way. You see, from here the branches come out, move along this way. From here the branches move along this way. This direction would help you to understand. So this helps you. Okay, so this is just intuition. You are still not confirmed if this diagram is correct. So we'll have the different things also. What is the angle of departure from the root locus branch? So this would again help you in knowing how would the closed loop poles branches emerge. So when we want to find out the angle of departure, what do we do? 0 minus sum of angles made by the vectors from other open loop poles plus sum of the angles made by the vectors from open loop zeros. This is your answer. Okay. So we want to find out all the angles and we'll find out. So how were the things here? Let's say this was 0, this was 0, here was, sorry, these were poles, here was 0, here was a pole, and we want to find out. So let's say we are calculating for this minus 1 plus j. What is the angle of departure? Whatever happens for this would happen, the same would happen for this in a symmetrical way. So let's find for minus 1 plus j, okay? So this is a 0. So first we want to find out the sum of angles made by vectors from other open loop poles. So let's check for other open loop poles only, okay? So we'll write angle made by vector from 0 to minus 1 plus j. What it is? 0 to this. What is this angle? So essentially you're supposed to find out this angle. What it would be? Wouldn't it be 135 degrees? Because you see, this is 1, this is also 1. So this is 45 degree. That means this pole is 135 degree. So this is 135 degree. angle made by -1 plus angle made by vector from -1 minus j to -1 plus j is 90 degree, right? So from here you can see this angle that is being made is 90 degree. Same goes for polar 0 also. So this is 90 degree. Angle made by the 0 to -1 plus j is also 90 degree. So what was the formula for angle of departure? It was 0 minus some of the angles made from the other open loop poles to the pole you are looking at. It is 135 degree plus 90 degree plus some of the angles from the open loop 0. It is 90 degree. You get the answer to be it would be 90 would cancel. It would be -135 degrees. See what is the answer corresponding to -135 degree in our option. It is 225 degrees. This is your answer. Okay. So from here you came to know what is the angle of departure. So if angle of departure is 225 degrees, I hope this is clear. Then we'll see the last part of this. Yeah, the closed loop system is stable for what values of k? So before coming into this question is stable for what values of k, I want to explain to you this with the help of MATLAB code. I will change the screen recording first. Just a second. MATLAB, okay. Just wait for a minute. Yeah, I present it to you. Yeah, I hope you are able to see this MATLAB window. So here in this case, this was a program that was discussed in the last class. So yeah. So what it really shows is uh, how do we work with MATLAB? I hope you are familiar. Even if you are not, it is a very simple program. So we essentially define the numerator and denominator. So what is our numerator in this case? It was k into s plus 1 upon s square plus 2s square plus 2s, right? So what we write? We write the coefficients here. So in the earlier class, this was the transfer function discussed. It was k into s plus 1 upon this whole thing. So you can see we in the denominator, the coefficient of s is 1. Okay. The coefficient of s to the power 0 is also 1. Then in the denominator, for coefficient of s cube, we have 1. Okay. For coefficient of 2s square, for s square, we have 2. S to the power 1, we have 2. And s to the power 0, we have 0. Because we do not have any constant coefficient over here. And we tried to find out what is the root locus. So this simple, so then we define a system. System is transfer function of numerator upon denominator. So you define the transfer function, then you can plot the root locus. So you say figure, it means that you're going to generate some figure. R locus of this system, R locus of the transfer function. Then you give a title, you give grid to be on, you can have other things also, where you can say x axis ka label ye hai, y axis ka ye hai. But let's see what was the result that time. Okay. So it was some sort of this. So there were similar poles, no? A pole is at origin, then a pole is at -1 plus j, pole is at -1 minus j, and a 0 is at -1. So you see, it's some sort of this thing happened that it went outside along the asymptotes at angle of plus and minus 90 degrees, and one of the poles converged to the 0. But in our case, what has happened? This region in which this line has been made from a pole to this 0 is not lying only on the root locus. So this was for k. This was a simple unity negative. This was a negative feedback system. And the other thing was that k was greater than 0. In our case, the thing is that k is less than 0. Now, if k is less than 0, my conditions are changed and I do not have anything over here. So I have this area lying on the root locus after this pole. I have this area lying on the root locus before this 0, but I do not have this midline. So what to do? So it would be changed. So see what would happen. So since I have k to be negative this time, I would put a minus sign here. I would put a minus sign here. And you see the transfer function is same. It just has k to be negative. So I'm including that negativeness here in the transfer function. And let's see what do we get. So it would be like this thing only for, I'll write here, for k less than 0. Okay, we're trying to do this. Now let's see what is the transfer function. Do you see? So we studied the same, no? Here there is a pole at -1 plus j. There is a pole at -1 minus j. Both of them move. Then they meet here at the break-in point at minus 1.5. At minus 1.5, one of them moves to infinity, one of them moves to a 0. Whereas the other pole, इसका भी तो कुछ करना है, ये भी तो किसी 0 पे जाना चाहिए था, पर हमारे पास एक 0 है, तो one of the pole has already moved to a 0 and one has moved to infinity. The other 0 will also move to infinity. Okay. So in the beginning, when we had started this question, this root locus, what we had said कि जब हम k को बढ़ाते जा रहे हैं, we would essentially see कि हमारा closed loop pole कैसे vary कर रहा है. अभी तुम देखो k हमारा लेस देन 0 है ऑलरेडी इस केस में, ठीक है. k इज ऑलरेडी 0, लेस देन 0 इन दिस केस. नाउ k इज लेस देन 0 का कंडीशन के बाद whatever you do, you see that okay, this pole will terminate at some 0 at minus infinity. This pole will terminate at 0, which is -1. Whereas this pole, कुछ भी हो जाए, अगर k नेगेटिव है इस सिस्टम के लिए, it would always be in the right half of the S plane. So essentially you see what is the behavior of closed loop poles from an open loop system. So you see here, this pole will always remain in the right half of the S plane. So closed loop behavior would be of this sort. If the closed loop behavior is of this sort, that it would always remain in the right half of the S plane, that means the system is not going to be stable. So the question that I showed you now was the closed loop system of problem 1 is stable for, so you had 3 options for all k less than 0. So for all k less than 0, you're not going to have. For all k less than 1, for all k less than -2, all sort of options. There was a fourth option, no value for k less than 0. तो k less than 0 के लिए ये प्लॉट किया है. अब ये पोल हमेशा राइट हाफ में है, तो it is not possible only. Understood? So that is why we would never have this
Screen is not visible, madam.
What is not visible?
Screen, madam.
Oh, you did not.
Your MATLAB
Yeah,
is a very
Oh, okay. Just presented the entire screen. Okay, I hope it is visible now. Just a second. I'll change the screen here also. Not getting an option over here. Okay, wait. Yeah. Okay. Um, yeah, you can see this. So yeah, I have to repeat this once more, but no problem. But did you see the last plot that I showed? Was that visible? I don't think it would have been. Okay, okay. I'll show you once more. So yeah, I'll show that. So in the last class we had this question. Okay, the numerator was this was a transfer function, right? For coefficient of s it was 1, and for coefficient s to the power 0 it was 1, and similarly for this case everything. And then we had seen the root locus. So this thing जो अभी हमारा केस में ट्रांसफर फंक्शन सब कुछ सेम है, ओनली थिंग इज दैट वी आर सेइंग दैट k is less than 0. We are saying that it is a negative this just a second. We said that it was a negative feedback system, but we said that k is less than 0, whereas earlier it was said that k is greater than 0. So you see this part of the root locus already lies on the real axis, -1 से लेके 0 pole wala. It lies on the real axis, whereas in our case this part is only forbidden क्योंकि we considered the case that the imaginary thing should lie. I hope on Meet it is visible, no? You are able to see this, no? Yeah. So we can see that it is very difficult to switch the screens. Okay, let it not go in the video. Here I'll explain you. So this part lies on the root locus. Now see this. We will do now for our question. So what would happen here is we'll place this to be -1, this to be also -1. Okay. When both of these are -1, both of these are -1. Why we have put -1 here? Because we want to see for k less than 0. So यहाँ पे -1 रखा. Here the equation remains the same. This is a transfer function only on which we were working, right? So everything remains same, and this is the transfer function over here. Now when we want to plot the root locus, what happens? What happens here when we plot the transfer function? So you see the same part which was lying on the real axis last time, because k was greater than 0 and it was a negative feedback system. Here in our case that is not the case, because this time we looked at that the number of open loop poles and open loop zeros to the right should be even. So this part is not lying on the root locus. Rather, we have the other parts lying. So you see the angle of departure for this was 225 degrees. You can see this coming to a point called minus 1.5. Similarly, you have symmetric behavior from the conjugate pole. Both of them are meeting over here, and from here you found out that there was a break-in point at minus 1.5. Sorry, so you're getting this value here, right? From here you can see there are two branches are deviating in two directions. One of them terminate at open loop 0, the other goes at infinity. Whereas for the second pole, which was at s is equal to 0, you have a pole, you have a branch that is going to infinity. So इससे ये तो पता चल रहा है कि एक पोल है उसका टर्मिनेशन 0 पे हो रहा है, ओपन लूप 0 पे, whereas two are going to infinity. Now the question that was asked to you was, the closed loop system for this problem only is stable for what values of k? So you see, this was for k less than 0, right? For k less than 0, if it is for k less than 0, how would the closed loop poles behave? So this root locus basically gives you that how the closed loop poles are going to behave if you are going to vary the parameter k. So you can see that these closed loop poles are always moving in the right half of the S-plane only. They are never going to move into the left half of the S-plane. So the answer there would be that it is not stable for any value of k less than 0. That is why we had this. Okay. Now, I'll change the screen. Okay. So your answer is no value of k less than 0. Right? The next question is, if one had positive feedback. So the question that I showed you and we had discussed in the last class as well, where k would be essentially greater than 0. In the problem with everything remaining the same, which one of the following statements is true? Okay. So what would happen? So if that were the case, what was happening? What kind of root locus you had? It was like it was going in this way, and there was a pole over here, there was 0 over here, and it was coming this way, right? So this was the thing that was happening. So you saw that all the poles, this pole goes to infinity as k tends to infinity. This pole also moves to infinity as k tends to infinity, whereas this pole at s is equal to 0 moves to this open loop pole, open loop 0 at s is equal to minus 1. So it never goes in this right half of the S plane. So if it were a negative feedback system with k greater than 0, then we would have the closed loop system would be stable for all k less than 0. Whereas in the previous question, it was not the case. Okay. So the last problem that we saw had negative feedback system with k uh, less than 0. Here, this is a similar kind of problem. It just has a positive feedback system and k is greater than 0. So what you can understand? So for negative feedback, you have 1 plus gs hs is equal to 0, right? I hope my screen is visible properly. Yeah, is equal to 0. Now, for positive feedback, we have 1 minus gs into hs is equal to 0, and this k is greater than 0. If k would have greater than 0, we would have to absorb the sign. Here we need not, because k is already greater than 0. So in this GSHS, k is greater than 0 and we have this case. So again, we are going to deal with the second case only. So it is a very similar kind of question, but it would rather have all the steps that we need for plotting the root locus. So then we want to find out for this question also, where are the open loop poles and open loop zeros. Please solve and let me know where are the open loop poles and zeros. Open loop 0 is clearly at 2. Where are the open loop poles? Factorize the denominator, you'll be able to find. Has anyone found out? This is very simple. You just had to.
Poles are -1 and -3, ma'am. Zeros are 2.
Right. Very good. So poles are at -1 and -3. So what we're going to do? Here is at -1. Here is -3. Okay. This is imaginary. This is real. Now we want to find out which region lies on the root locus for this. So it is again the same thing where you want to find out that if you choose a test point, let's say I choose a test point here. Okay, it is somewhere here, then this would lie, right? If I choose a test point in this region, this would not lie. If I choose a test point here, this would lie, because if the test point is here, you'll have two open loop pole and zeros, real open loop poles and zeros to the right of it. So this would be included in the root locus. This would not be included, as you just have one point to the next of it, and here this would again be included. So your question is, which of the following statements is true, right? So which portion does lie on the root locus? It is -3 to this portion again does not lie. Mark it. So -3 to -1 lies on root locus. So this is your answer to this question. Now, yeah, which one of the following statement is true about the locus of closed loop poles? So it basically asks you something related to the asymptotes. So first you should make sure what is the number of asymptotes. So how do you find out the number of asymptotes? It is n minus m, right? And what is n minus m here? It is 2 minus 1. So you just have one asymptote over here. Now, if you have one asymptote over here, you would have to find what is the angle. Angle of asymptote. It is plus minus k into 360 degrees upon n minus m. Okay. Plus minus, so n minus m is anyway going to be 1. And here it is k into 360, where k can range from 0, 1, 2, and so on. Since the number of asymptote is only 1, we'll just have to deal with one value, and it would directly be 0 degree. So what do you get? The complete positive direction of the real axis is going to lie on the root locus is going to lie in that region. So not root locus, the asymptote is going to lie there. So the complete positive x-axis serves as an asymptote. Now what we are going to do? So if there is just one asymptote, it is going to have some intersection also, where it intersects with the real axis. So we are supposed to find that point. So if you try to find out the point of intersection with the real axis, it is sum of open loop poles minus sum of open loop zeros upon n minus m. So this would give you -6. So there is only one asymptote which would be on the positive real axis. Now, so what is the answer? It would not have, what was your answer for this question number 8? It would have positive real axis as the only asymptote. So essentially we have used this formula. No, we haven't used this formula.
The meaning I didn't understand, ma'am. The option meaning.
Yeah, I'll tell you. Just a second. Plus minus 360 degrees k upon n minus m. So what number of asymptote do you have here? it is clearly 1, right? So we are going to deal with any one of these only. Now, when you try to find out the angle, what did you get? It to be 0 degree. Okay, that means that what is 0 degree? This direction. So that is only written here. It would have the positive real axis as the only asymptote. So there is one asymptote which is along the positive real axis. From this 0 degree, we have found this out.
Okay, ma'am. Ma'am, negative real axis means?
Negative real axis means along this direction.
Okay, okay.
So we had this in the earlier question, no? Negative real axis and positive real axis both. They were the
Yes,
asymptotes
yes.
there.
Yeah.
Yeah. Now, yeah, we want to find out where is the breakaway or where is the break-in point. See, you can have the possibility of breakaway point also, break-in point also. Anything is possible. So, if you see the diagram, so both of these are poles together. Definitely, दोनों से branch emerge करके, there is going to be a breakaway point where, how this would look like, I'll show you. See, there are two poles. It would come in this direction. It would come in this direction. Kyunki two poles are going to repel each other and you don't have any zero in between. So there is definitely a breakaway point here. So you'll have the things moving in this way. Okay. But you also have a scenario that there is a zero. तो अगर जीरो है तो कुछ तो ऐसा होने वाला है जिसमें कोई एक पॉइंट जो है वो जीरो पे टर्मिनेट होने वाला है और ये जो एसिम्प्टोट ऊपर ये जो ब्रांच ऊपर राइज किया है फ्रॉम द ब्रेकअवे पॉइंट ये कहीं तो इन्फिनिटी पे जाने वाला है. दिस इज द हिंट दैट वी हैव अप एंटिल नाउ एंड नथिंग एल्स. बट दिस इज फॉर श्योर दैट कि एक ब्रेक अवे पॉइंट अकर होगा. अगर ये ब्रेक अवे पॉइंट अगर नहीं भी होता तो देयर कुड बी सम सिनेरियो जिसमें ये पोल जो है इस जीरो पे टर्मिनेट करता और ये पोल कहीं से तो इन्फिनिटी पे जाता, विच इज डिफिकल्ट. पर ये भी हो सकता है. सो इन दैट केस आल्सो वी नीड टू चेक दैट इफ इट इज क्रॉसिंग द इमेजिनरी एक्सिस और नॉट. सो विल सी द स्टेप्स one by one, but let's start from here. Okay, so where is the breakaway point? First we'll find out. So we had already seen that it can be written as 1 plus k into as upon bs is equal to 0. So this gs into hs can be written as as upon bs, right?
Madam,
Yes,
from -3 to -1, there will be a breakaway point, no, madam?
-3 to -1. Just a second. Yes.
So only option possible is -1.87, madam.
Yeah, you can say that, but I guess you should solve. Means
Okay, madam.
if you think if there are no breakaway points, then means I said the other scenario that a branch originates from this pole and comes till here and this pole follows and the branch from here follows some other path to infinity along this asymptote, which is anyway not possible. But if it were a case like this, so intuition is really good that it should be somewhat in that area only. But if you have multiple options in between -1 and -3, then you will not be able to
Then you have to solve,
you
madam.
should essentially know how to solve it, so it would help you.
Yes, madam.
Okay, so when you try to solve this, so it would be a dash s into bs minus b dash s into as is equal to 0. So when you try to find this, okay, what was your as upon bs? I guess someone is unmuted. Let me mute. Yeah. So what we are going to do? What was the question here? K into s minus 2. I'll copy this. s minus 2 upon s square plus 4s plus 3. No, yeah, it was this, and it was s minus 2 only. So if you try to find out a dashes, what would you get? It would be 1. B dashes would be 2s plus 4, right? Try to find out what you get corresponding to this equation. It would be some polynomial, coefficient of s square plus something coefficient of s plus something this coefficient of s to the power 0. And let me know these coefficients. Since we are going to get 2s, right? Something and something. We will check कि इन दोनों s के corresponding whatever s we are going to get, if we put this in this characteristic equation, okay, if we are going to put this s in this characteristic equation, the k that we are going to get is positive or negative or imaginary. If it is positive and real, that means that this is either a break-in point or a breakaway point for sure. So we first need to know, so what are the roots of this equation, or the coefficients before that? When you try to find out the coefficient, it would be 1, minus 4, and minus 11. Okay, and the s that you're going to get is approximately 5.87 and minus 1.87. Okay, you can verify this yourself that you're getting. Now what we need to check is, for s is equal to 5.87 and for s is equal to minus 1.87, for both of them, what is the value of k? We need to find out. So how we'll find out? So from this you can write k is equal to minus of s square plus 4s plus 3 upon s minus 2, and substitute s is equal to 5.87. What will you get? Whatever you get, it would be something greater than 0. It would be 15 point something, but it would be greater than 0. Similarly, when you do for this case also, k is equal to what, and you find out k is what for s is equal to minus 1.87, here also you'll find that you'll get something greater than 0. That means ये दोनों पॉइंट कुछ तो है, ब्रेक इन पॉइंट है या ब्रेक अवे पॉइंट है, कुछ तो है, क्योंकि इन दोनों के वैल्यूज ग्रेटर देन 0 मिल गई है. पिछले केस में इट वाज s के 3 वैल्यूज थे, वन वाज सम रियल वैल्यू, सम पॉजिटिव रियल वैल्यू, टू वर इमेजिनरी. इमेजिनरी के करस्पॉन्डिंग वी कुड नॉट गेट अ ब्रेक अवे और ब्रेक इन पॉइंट in the last question. Here we are getting for both the values of s, we are getting a breakaway or break in point. Okay, so as Surya already said there, that this from the option it is already clear that so there was a 0 here, minus 1 and minus 3. So कि यहाँ पे तो दो पोल है, तो यहाँ पे ब्रेक अवे पॉइंट आ जाएगा. So this is at minus 1.87. You get another information that there is some sort of thing at this point also, s is equal to 5.87, which is beyond this point. यानी यहाँ पे 5.87 पे भी कुछ होना है. अभी वहाँ पे क्या हो सकता है? what all could be the options कि यहाँ पे 5.87 आए. तो one thing could be कि एक पोल इधर से चल के आ रहा है, एक पोल इधर से चल के आ रहा है, they both diverge. Okay, diverge करके they move, I'll draw it more clearly, they move along this to come here, it moves along this to come here, फिर ये इधर, ये towards infinity, this direction, this direction, this direction, this direction. This could be the cases, right? So this would act as break away point. Q, because it has originated from the pole and the both of the branches have split apart, whereas in this case it is break in point because the branches want to come closer to 0 and one of them moves to 0, the other moves to infinity. So this is the case happening here. Okay, so this is some sort of root locus that you are going to get from here. So the other questions that follow here are relatively same. So that in problem 7 the value of k at breakaway point is, what is the value of k there? Okay, I did not tell you the values of k here, no? Okay, you can just verify this on yourself, but I'll tell you the answer here. So for 5.87, this k is going to be 15.746 and here it is going to be 0.254. Both of them are positive. Okay. So you see the k at the breakaway point is, what is it? 0.254. The break-in point is at what? 5.87. We already saw. And the value of k at the break-in point is, what was the value of k? It was 15.7, right? So all of these questions are solved. So I essentially took all of the questions in one question only. Then, so you saw that, okay, this was my root locus, where this was a 0, a pole was at -1, a pole was at -3. It was this sort of root locus. Then we want to know, acha, this has crossed the imaginary axis. Then what is this point where it has crossed the imaginary axis? This is called crossover point, where it crosses the imaginary axis. So if you want to find out what do we do here, we write the characteristic equation first, okay? So it is 1 minus k into s minus 2 upon s square plus 4s plus 3 is equal to 0. Then you put it in the form of characteristic equation. It would be s square plus 4s plus 3 minus k s plus 2 is equal to 0. Now, because we want to find out ये point of intersection क्या है, तो
s minus 2 madam.
Sorry?
S minus 2 madam. S square plus 4s plus 3 minus k.
S minus 2, right?
Madam, putting j omega, s is equal to j omega and solving we don't get, madam.
Why do you not? You'll get. I'll show you. Put s is equal to j omega over here because we want to find out किस point पे intersect कर रहा है. तो इन दोनों points पे कोई real value नहीं है. It is just the imaginary value. So you'll put s is equal to j omega. What you'll get here? Minus omega square plus 4j omega plus 3 minus kj omega plus 2k is equal to 0. Okay, spread out the terms. Imaginary alag, real alag. 2k minus omega square plus 3 plus 4 omega minus k omega into j is equal to 0. ठीक है, अभी हमको क्या पता करना है कि यहाँ पे ये पॉइंट क्या है जिस पे ये हुआ है. ये पॉइंट पता करने का मतलब कि रियल पार्ट शुड बी इक्वल टू 0. तो इसका रियल पार्ट को 0 करो. ओके, सो बिफोर मेकिंग रियल पार्ट 0, अगर इसका रियल पार्ट 0 किया, हाँ, रियल पार्ट 0 इसका
k is equal to 4 madam.
Sorry?
K is equal to 4 madam.
Right.
Including the imaginary part. K is equal to 4, madam, equating the imaginary part.
Right, right.
K is
So
equal to
if
4 and substituting in real part.
yeah, 4 omega minus k omega is equal to 0. From here you will get k is equal to 4. So you know that k is 4. So 8 minus 4, 8 minus omega square plus 3 is equal to 0. 11 is equal to omega square. That means omega is equal to root 11, which is approximately equal to plus minus 3.32, right? 3.32 J. Am I right or not?
Yes, madam, you are correct, madam.
Wait. This should not be J, no? Okay. So what is your frequency? Your frequency is plus minus 3.32. And if this is the frequency, matlab 3.32 J. So essentially the crossover points are what? Your crossover point was plus minus 3.32. Since it is on this axis, it is going to be definitely J. So you get this to be answer. Make sense? These both are the crossover points. तो हमें पता चल गया कि ये रूट लोकस इमेजिनरी एक्सिस पे किधर इंटरसेक्ट करने वाला है from this. And the next question that you have is the value of k at crossover point. So you already found that k is equal to 4, right? From here. So that is only the value. Then the closed loop system is stable for what? This is your question. So okay, I'll tell you, but before that,
K less than 4, madam.
yeah, k less than 4, and we'll see this in MATLAB also. But before that, you could say k less than 4 because if you move, okay, I'll show you why it is k less than 4 again. But before that, if I asked you to confirm this k less than 4 with the help of Routh-Hurwitz stability criteria, would you be able to do? Would you be
Yes,
able
madam.
to say this is the answer?
Yes, madam.
Yeah, right? Because what would be the characteristic equation? So here in our case, your characteristic equation was k upon in s square plus 4s plus 3, right? This was your characteristic equation. You wrote s square plus uh, s square plus 4s plus 3 minus ks plus 2k is equal to 0. S square plus uh, plus 4 minus k s plus 3 plus 2k is equal to 0. What should happen? Iska coefficient should be positive. Iska coefficient should be positive, rather should be of the same sign. So for s square, if it is positive, it should be positive for all. This should be also positive. So this would be positive if k is, this would be positive if k is less than 4. This would be positive if 3 plus 2k is greater than 0. That means k is greater than 3 by 2. दोनों का intersection लेके it should be, sorry, k, k should be greater than minus 3 by 2, right? You would know that it is, this condition is important or not. Have I made some mistake? Check this condition. K should be greater than minus 3 by 2. मतलब k should be less than 3 by 2, and here it says k should be less than 1.5, and here it is k should be less than 4. When you take the intersection, you'll get k should be less than 4. So you get k should be less than 4 here. You could have done similar thing in the last question also. When we said कि हमें stability जानना है, what was that question? In question number 6, I believe. No, it was 5, I think. Yeah, for no value of k. Try to do this question with Root-Hurwitz stability criteria. From there also you'll get k to be less than, for k less than 0, nothing is possible. It has to be k greater than 0. So you'll get the same thing. You can check this. Please check this today. Okay. It would be a very similar approach, same characteristic equation, and then you'll have to find out using Root-Hurwitz stability criteria. And since it is a second order polynomial only, you just have to check if all the coefficients of s to the power something are of the same sign or not. That's it. Okay. So this was the last question where we wanted to say that problem 7 is stable for all k greater than 4, k less than 4, or whatever. So I'll share the screen again. Okay, so if you see this was our last example. Now what is our question? Yeah, it is s minus 2. So that means it is 1. This is minus 2. And here in the denominator it is 1, 4 and 3. 1, 4 and 3. Because it is now second order, it is not third order. But since it is a positive feedback system, we want to, क्योंकि ये जो सिस्टम ट्रांसफर फंक्शन न्यूमरेटर अपॉन डिनोमिनेटर जो होता है, this is for negative feedback. Okay, this is for negative feedback. So if you want to take into account positive feedback, you'll have to multiply this with minus 1. If you multiply this with minus 1, both the numerator and denominator, you are actually taking in the minus sign. तो पिछले बार क्योंकि k negative था, we included the minus sign. This time it is a positive feedback system, so we are taking the minus sign inside, and now it is a positive feedback system. And then we'll plot the root locus. So this time your transfer function is s minus 2. There is no term for this. It is s square plus 4s plus 3. And then we want to see what is the root locus. And here k is positive. It's not negative now. Okay. We'll generate the result. Okay. Let me change the recording screen also. Yeah. See this. We had a pole at minus 1. You all had said we had a pole at minus 3. We added 0 at plus 2. Both of these poles move in the same direction. There is a breakaway point over here at minus 1.87. The locus diverges. It diverges in both the directions. Then at plus minus 3.32, यहाँ पे देखो ये 3.32 है, ये minus 3.32 j है, यहाँ पे crossover point मिलता है, then it moves here. We had got another break-in point at 5 point something, 5.8 or something. It was no 5.2 or something. No, it was 5 point what? Can someone tell me what it was? Yeah, 5.87. At 5.87, it is the break-in point जहाँ पे दोनों locus आकर मिलता है. One of them goes to the open loop 0, the other goes to infinity. So, since you are trying to solve many assignment problems and you are also trying that I want to see if my result is correct or not correct, this R locus is a very handy function. So you can always cross check your results from this. Once you derive it with your hand, you find out everything, and then you can always use this to see if you are getting the answers correct or not. Just a second, just a second. I'm sorry. I hope my screen was visible when I was showing you this. Yeah. So this would always help you in finding out what is the correct root locus. So yeah, we are done with all the questions today and hope you have a clear understanding of how we construct the root locus plots. So that's it. Next time we'll have new concepts started. Yeah.
Hello, madam.
हाँ बोलो.
Madam, if I called ATM, madam, and I also mailed, but
Just
no
a
one
second.
is
I'll stop the. Okay. So continue. You
but
called
no one is
ITM.
responding, madam. Yes, ma'am. I called ATM and I mailed also, madam, but no one is responding, ma'am. Can you search and tell me how is the model paper and how is there a negative marking for each question and how is the model paper, madam?
Okay.
Question paper negative marking is there. Then how many questions and what time? Can you tell, madam?
Okay. You did not get any reply from after mailing them, right?
Yes, madam.
Okay. I'll see. I'll try to find out and let you know in the next session.
Thank you, madam.
I think there would be negative marking, but I'm not sure exactly, and definitely it would be MCQs only. But yeah, since we are TAs for the session, we are not sure about this, but I'll try to find out.
Okay, madam.
Okay.
Thank you, madam.
Okay. So we can end the session today and hope everything made sense. Please try out the questions in your assignment. The questions would be of these sort only, and it would be following the same type of like the same algorithm for solving the question you can follow. So yeah, we are done with the today's session. Thank you.
Thank you, ma'am.
Yeah.